Ladies and gents, well, we're going to continue talking about the electromagnetic spectrum. We are going from long wavelengths towards shorter wavelengths. We've talked already about radio waves, AM radio waves that are quite long, many football fields in length, FM radio waves which can be many feet in length. Now we're going to talk about microwaves and your cell phone waves. Now, as you can tell by their position, these are going to be shorter in wavelength, and that's going to affect how they act. Cell phone waves are actually a type of microwave. How long is one cell phone wave? It's about 6 to 15 inches long. So you know how long a ruler is. So it's about half a ruler to about a ruler and a bit long. Not that long at all. Cell phone waves are line of sight, meaning you have to be within a straight line shot, or not you so much as the electromagnetic waves of your cell phone, have to be in a straight line shot to a cell tower in order for that tower to pick up your cell phone signal. How the heck do you talk to a friend or a relative that happens to be on the other side of the planet? Well, it's a wonderful and cool thing. If you're standing someplace talking on your cell phone, the cell phone signal is going to go up to one of these cell phone antenna that is actually going to pick it up. Then it is going to transmit that signal up to a satellite. The satellite is going to then travel to another satellite and then another satellite and another satellite. The signal gets transported around the big Earth that is this big round ball, and then that signal gets downloaded to another antenna, and that another antenna then transmits that signal to somebody else's phone. It rings and they pick up in Kuwait or Afghanistan or wherever they may be. Pretty magical and wonderful thing. But we could not have this if we didn't have all of these geosynchronous satellites orbiting the Earth, because electromagnetic waves travel in straight lines. If you have terrain issues like big hills, that is going to block some of your cell signal. That's definitely going to be a challenge. Now, modern cell phones, you don't see the antennas. The antennas often are internal. Usually they're internal. And this is a picture of an antenna inside of a cell phone. This is actually called a fractal antenna. The antenna is kind of folded up on itself. And amazingly, that crazy little beast works, and works very, very well. We've all had challenges getting cell phone signals. Some of the things that will have a bad effect, of course, is terrain. If you're living here cuddled up next to a big hill and the cell phone antenna is on the other side of the hill, you're not going to get that cell antenna. If you would live in a highly populated area like in New York City or in Los Angeles or in Chicago, they will have multiple antennas every few blocks. One, because of the high volume of traffic. The other reason is because of the fact that large buildings are going to block cell reception. If you are inside of a metal building, the metal building is going to act like something which is called a Faraday cage. A Faraday cage is just a metal cage, and it was discovered by Michael Faraday, a scientist in the late 1800s, and he found that these metal mesh was so close together that radio signals couldn't get out. It was kind of like a mirror to radio signals. And if you have big metal walls and you're in a big metal building, no radio signal is going to get in and no radio signal is going to get back out. Some of them might squeak through a window, but most of the time they're not going to get in and out very well at all. One of the questions I've gotten asked many times are, do cell phones cause cancer? Is this going to be something you should worry about? And I applaud anybody who's worried about their health. I think it's something we should all take into account. But let's talk about the math of the situation. In order for any one of these electromagnetic waves to hurt someone, they have to be ionizing radiation. Now, what do I mean by ionizing radiation? To make an ion, you've got to take an atom, and a burst of energy has to have enough energy to kick out an electron. If it has enough energy to make an electron leave, then it is ionizing radiation. So how much energy does that need to be? Well, basically, if you remember, the radio end of the spectrum, these are low energy, and by the time you get to the far other end, these are going to be the high energy kinds of electromagnetic waves. The higher energy ultraviolet, the X-rays, and the gammas, these are actually ionizing radiation. They have enough energy to cause electrons to be knocked off of atoms, creating ions. Now, why is that a big deal? Once an atom has been transformed into an ion, it has a very bad habit of bonding wherever the heck it wants. It can just, instead of bonding where it's supposed to, it just does a lot of wacky and crazy bonding. A lot of it your body can heal, just kind of like your body heals from a paper cut. But if it happens to be an electron on a piece of DNA that tells a cell how to reproduce, it's possible that it could cause a mutation, and mutations can possibly lead to cancers. So can electromagnetic waves hurt you? Yes, but it's the short, high energy ones that are the ones we worry about the most. And waves that are 6 to 15 inches long just do not have enough energy to go kablam and knock an electron off an atom. Now let's talk about microwaves we use for cooking. Interesting story about their discovery. Back in World War II, an American scientist named Percy Spencer was actually doing some research on radar, radio detection and ranging. They wanted to come up with a way of looking at the sky and not seeing just clouds, being able to penetrate through the clouds. So they came up with the idea, let's use a shorter wavelength than radio waves, which are long wavelength, and they started using microwaves. Well, as Percy Spencer was doing this military work and exploring this way of seeing through the clouds for pilots and for incoming missiles and things like that, very often he would have a chocolate bar in his pocket. And he noticed that whenever he played with certain frequencies of microwaves, his chocolate bar would get soft, extra soft beyond just being in his pocket soft. And so he would do some experiments, and he would put the chocolate bar in the path of microwaves, and they would melt. And he went, that's really, really interesting. After World War II, he came home, went back to his native Iowa, and in the Amana colonies, which is an area of many small towns in Iowa, he created a company to produce the very first microwave oven, and he called it the Amana Radar Range. Now, back in 1967, it was a long time ago, it cost about $500. This was a huge and very expensive novelty. People did not have $500 microwaves in their homes. High-end restaurants and things like that could afford a microwave, but this was brand new technology, and not everybody had it immediately. How big are these microwaves for cooking? Well, they're about 5 inches. They're a little bit shorter than the microwaves that are used for cell phone technology. Now, a lot of people suspect that microwaves and metal don't mix, but I've also had this question asked to me very, very often. If you cannot put metal inside of a microwave, how come the walls of a microwave are made out of metal? Metal actually acts like a mirror to microwaves. There is a gizmo up here called a magnetron, which is a little radio transmitter that produces the microwaves. The microwaves get bounced around the metal walls inside of the microwave, and eventually those bounced waves hit the food that you are cooking. If you do not have a carousel that rotates your food, one of the things you probably noticed in your microwave oven is you will have hot spots and you will have cold spots. And the reason is because where these waves naturally bounce all the time, you're going to get hot spots. Now, how does the rest of the food get warm? Well, the rest of the food gets warm by conduction, the transfer of heat by touching. And so you're going to have hot spots and cold spots. And I don't know about you, but I've read recipes where they say, take your casserole out and stir it once in a while and then put it back in. And that's because of this. But if you have a carousel, it's constantly rotating the food through the hot spots and cold spots. Now, the door of a microwave is one of my favorite things in the world because it's so cool. If you look at it really, really close, it's kind of like a mesh. it has little holes in it. And one of the things that's so cool about the mesh on the door of a microwave, it gives you a real visible representation about the difference in size. The door on the microwave, the holes are large enough to let visible light out because you want to look inside and see your burrito cooking. But the holes are so small that the microwaves can't get out. So the microwaves are reflected back into the oven and they just cannot get out. It's kind of like for the microwaves, like you're trying to bounce a beach ball off of a screen door. They're not going to get out the little holes. If you've ever had a metal bread tie or you accidentally put a fork or something in a microwave, you're going to go, but that sparks. Okay, yeah, the walls are made out of metal and the front door is made out of metal, but I've put bread ties in there and I get sparks all over the place. What happens? If you have tiny little thin pieces of metal, like the tines of a fork or a bread tie, you're going to get lots and lots of vibrating electrons in those skinny little pieces of metal. That will cause a massive amount of heat. You can get sparks, and that can then start fires. Now, microwaves actually cook your food because they're the right size to vibrate or oscillate water molecules and fat molecules. So only foods like butter or fat like eggs that have fat or anything that has a water content, those things are going to oscillate back and forth and back and forth. And it's that back and forth oscillation or vibration that's going to create the heat. Dishes typically do not contain a lot of water content or fat content, and that's because of that you can use plastic dishes and Corelle and different things like that in your microwave without it actually damaging those. One of the questions I've been asked very often is, do microwaves cook from the inside out? And they don't. They only penetrate about a ½ inch into food. But if you try and do something like cook a hot dog or melt butter in there, it looks like it cooks from the inside out. But that's only because you're dealing with something that is very, very skinny. And so the middle gets twice as many microwaves. And so the middle has a tendency to get a little hotter because it's sort of getting double heated. If you try and cook something big like a turkey in your microwave, and I don't know anybody in a long time that's tried to cook their Thanksgiving turkey in the microwaves will only penetrate about a ½ inch, and then you've got to put foil around that turkey and let it sit, and then let the heat seep into the center of that bird via conduction. All right, that will do with microwaves. We're going to come back next time and keep talking about littler waves.